Welcome to Team 5's presentation on Milestone 3 analysis. I am Usha and my teammates are Sadaf and Tanya. In the run-up, we discovered that the variables in our initial loan dataset were not strong predictors of the loan interest rate, so we infused new variables. From Milestone 2 analysis, the random forest regression model and the relationship classifier stood out as the best models to predict loan interest rate and the outcome class for the occupancy status variable. One of the reasons why we could not achieve desired accuracy rates for classifiers in Milestone 2 was our imbalanced dataset. For this milestone, therefore, we downsized our dataset by undersampling the dominant classes. Where required, we used normalization to pre-process numerical variables and performed one-hot encoding on categorical variables to suit the requirements for the algorithms. For the linear SVM model, we use the KSVM function and the vanilla.kernel. This function uses the one versus one approach to train binary classifiers, where each classifier distinguishes the best between two classes, and the final result is produced based on the majority vote. Support vectors are the data points used by the SVM model to define the optimal hyperplane that separates different classes of the outcome variable in the feature space. The diagonal values in the summary table indicate the accurate predictions made for each class by the linear model. The overall prediction accuracy for this model is 60.43%. Precision focuses on the positive predictions made for a class. It answers the question of all the instances that the classifier predicted as positive for a class, how many are truly positive for that class? In our case, the prediction rate is 57.26% for I class, 69.33 for P, and 54.03 for S, which are not very high. The model needs fine-tuning using methods such as feature selection. Recall our sensitivity provides an answer to the question that for all the actual positive instances for a class in the dataset, how many did the model identify correctly as positive? Recall values are slightly higher than prediction values for the model, indicating that many of the instances that this model identifies as positives are actually negatives. Specificity answers the question of all the actual negative instances for a class in the dataset, how many did this classifier predict correctly as negatives? F1 measure is the harmonic mean of precision and recall and provides a balanced approach to model evaluation. Based on all the metrics for the model, we can say that our model is better at classifying P class, even though we trained the model using an equal number of observations for all the three classes. We found that when we trained the SVM as a nonlinear model using the RBF kernel, the model overall accuracy decreased by a slight percentage, and there was no noticeable improvement in other performance metrics either. To summarize, even though the SVM model returned better classification results than logistic, naive-bayes, and division tree classifiers, it cannot be ruled out that an important reason for this improvement could be that we used a more balanced dataset to train the SVM than the one we used to train Milestone 2 classifiers. We trained a neural network as a regression model to ascertain that this model could give better prediction results for the outcome variable loan interest rate. In our neural network model with default values, we have one input layer with 92 neurons for 92 encoded independent variables and one hidden layer with one neuron. We have 93 weights associated with 92 neurons in the input layer and the one neuron in the hidden layer. We have one bias term for the hidden layer neuron. There are a total of 94 neurons in this model, which includes the output neuron. Each neuron has its own activation function. This algorithm uses a logistic sigmoid function, calculates the value of the activation function to be passed to the neuron using the weighted sum. The error function, also known as the sum of squared errors, is 11.42 for this model. This is the plot of the neural network regression model, which returned a correlation of 0.757 between actual and predicted values and an RMSE of 0.128 using default number of hidden layers. This table represents the summary of important metrics returned by different neural network models trained with different number of hidden layers and used to predict the outcome variable. The best performing model is identified in green. This is the plot of the best model, and it returns slightly better correlation value than the model with default hidden layers. In summary, neural networks with more hidden layers did not show significant improvement in predicting the DV in our case. My teammate Sada will take over and talk about clustering techniques.
Hi everybody. So in the exploration of clustering techniques, we first employed the PAM clustering methods. To account for our mixed data types, we utilized the DAISY function, which calculates go-over distances. By inputting the dissimilarity matrix into the PAM-K function, we discern that a dataset is optimally segmented into two clusters, one with about 1,145 elements and the other with around 1.6K elements. A comparative analysis of the clusters revealed a notable pattern. For numerical variables, cluster 1 showed consistently higher mean values. However, for nominal variables, such a clear distinction between the clusters was not so evident. The silhouette plots on the screen here illustrate these clusters. These plots do not come inherently with PAM clusters, but rather serve as a strong visual cue to the quality of a clustering, showing off how the algorithm iteratively brought together data points to form two distinct clusters. With these insights, we've established a foundational understanding of a data structure through PAM clustering. Next, we'll compare these results with those from other clustering techniques to see how our data behaves under different algorithms. The analysis of mean values highlighted a very clear disparity. Numerical features in cluster 1 showed notably higher means, particularly the original interest rate, as you can see here, which differed by 0.82% from cluster 2. Contrastingly, nominal variables did not exhibit a pronounced division across clusters, suggesting that a clustering was more influenced by numerical data. As you can see in this slide, box plot visualizations were employed by us to further compare feature distributions, confirming that features like the original interest rate present more marked differences between clusters compared to others. Coming to hierarchical clustering, it revealed distinct data groups using complete single and median linkage methods, each with its unique dendrogram as seen here. Complete linkage formed tight clusters and were outlier sensitive, while single linkages showed elongated clusters prone to noise. Median linkage, on the other hand, were less influenced by outliers and offered a balanced cluster structure. Optimal clusters were identified by a notable increase in dendrogram height at the second level, suggesting two main clusters. These methods' visual representations provide insights into the interesting data groupings and guide our cluster selection strategy. In hierarchical clustering, optimal clusters were identified at a dendrogram height of 0.75, separating the data into two main groups, with the first cluster holding 1,330 elements and the second 1,430 elements. A significant finding was the larger mean difference in original interest rate between clusters at 1.09%, surpassing the 0.82% observed previously in PAM clustering, suggesting that hierarchical clustering provides a more defined distinction among clusters based on a key variable of interest. Now turning to DB-scan clustering, we fine-tuned the epsilon value to 0.18 and set the minimum points to 7, aiming to reduce noise points. This approach yielded one large cluster with 2,581 elements and a small second cluster with only 5 elements, leaving 174 outliers unclustered. The means comparison showed less distinction between clusters than PAM and hierarchical methods, indicating DB-scan's limited differentiation capacity for our dataset structure. A comparative analysis of clustering techniques highlighted that hierarchical single and complete linkage methods are concurred on the first cluster with 1,329 data points, yet differ completely on the second. A similar pattern emerged when juxtaposing hierarchical complete linkage with PAM, sharing common ground on about 1,057 and 1,342 data points for the first and second clusters, respectively. Contrasting hierarchical single linkage with DB-scan revealed a complete agreement on the first cluster with about 2.5K points, but none on the second. Lastly, PAM and hierarchical single linkage methods aligned on 1,144 points for the first cluster, but diverged on the second. These cross-method comparisons really underscore the variability and alignment of clustering techniques which were applied to our dataset. The next part will be handled by my teammate Tanya.
Comparative analysis. In our K-fold cross-validation analysis, random forest consistently outperformed other models in mean accuracy, demonstrating its robustness. Decision trees showed accuracy but with variability, while support vector machines and neural networks lagged behind. Box plot and dot plots confirm these trends, especially highlighting random forest reliability and neural networks fluctuating performance. The kappa statistic further reinforced random forest strong predictive power. Now, with repeated k-fold cross-validation involving 3 runs of 10 folds each, random forest again emerged as the top model, showcasing high accuracy and consistency. Decision trees displayed potential but with more variable results. In contrast, support vector machines and neural networks showed lower accuracy. Visual analysis using box plot and dot plot revealed random forest high median accuracies and low variability, distinguishing it from the less stable neural networks. Kappa scores highlighted random forest to superior balance of accuracy and predictive agreement. Now, we analyzed cross-validation using bootstrapping with 30 runs, applying an 80-20% train test split. Results showed random forest as the most accurate and consistent model. Decision trees were effective but less stable. Support vector machines and neural networks lagged in accuracy, with NN showing significant inconsistency. Kappa values confirmed RF's reliability and DT's variable performance, with SVM and NN being less stable. Box plot and dot plots at a 95% confidence level supported these findings. Now exploring filter feature selection in linear regression, we found bond rate and Fed fund rate as key predictors for original interest rate, with LTV and CLTV being almost identical. Our refined model explained 37% of the original interest rate variation, a notable achievement for complex financial data. Cross-validation revealed RF's superior performance over neural networks, which suggested overfitting. Now we deployed recursive feature elimination method, which is a hybrid of filter or wrapper methods on a random forest model. Since we deployed random forest algorithm as a regression model to predict our DV original interest rate, feature selection was based on RMSE values. The number of variables with least RMSE turned out to be 6, as is evident from the graph. Now, we used our original RF model trained using original training data with all IVs to predict the original interest rate using test data and found a correlation of 0.69 and RMSE of 0.63. With the model retaining only important features, we found correlation value of 0.67 with RMSE of 0.43. To summarize, with an insignificant reduction in correlation of 0.02, we achieved a significant reduction in RMSE of 0.43 with huge gain in reduction of complexity of the model. Now we applied regularization in neural networks to improve the model's performance. Initially, our model had a correlation of 0.7. Introducing RPROP for regularization, the correlation improved marginally and indicated enhanced model generalization and slightly better accuracy. Now, using stepwise forward selection on a linear model, we started with the base model and iteratively added variables to reduce the AIC. The final model highlighted key predictors like bond rate and Fed fund rates, and unexpectedly variables like occupancy status and seller names, revealing insightful patterns in interest rates. These are the references for our milestone 3. Thank you.